In this video, we're going to do some principal component analysis with a very large data set. We're going to use the MNIST data set, which is a bunch of handwritten numbers. And we're going to combine our PCA approach, our principal component analysis, with a classification model where we know that this picture is a 4. And so we can create an algorithm that will identify images and identify what number appears in the image. So to build that, we have a very large data set, 10,000 handwritten numbers. And for each picture, there's actually 784 variables, and that's because we have a 28 by 28 image, and so there are 784 pixels or squares in it. Now, because the database is so big, we're going to do what is called incremental PCA. We're going to add the data in batches to do our principal component analysis to take the 784 variables and simplify it down using dimension reduction. So keep all the variability that's in the data, but don't keep all the 784 variables, so that we can still then identify which picture is a 4 and which picture is a 6. So how do we do this? Well, we are working through the workbook that you will find here under drstephpowers.github.io/BIA, dimension reduction here. Go in there and you will find access to the workbook. So let's go into the workbook. All right, so the first thing you want to do is you want to import this big data set. You can do it from the sklearn datasets. So from sklearn.dataset import fetch_openml, and then we're fetching the MNIST 784 version 1. That is what we'll call MNIST, and we'll actually relabel that so that we'll take the data from it, and actually we'll just take 10,000 of the data points from it. Okay, so we've loaded it into the system. Now we're going to use the package Incremental PCA so that we can load it in batches to do our principal component analysis. We're going to use standard scalar here to standardize our data. Good practice to get into when you're doing your principal component analysis. We're going to import matplotlib.pyplot as PLT so that we can show this, because we want to actually create these images, assemble them from the pixels here. And then we're going to import numpy as NP because we're going to do a lot of manipulating of the data into different formats. So for example, let's say that we pulled from this data set X the index location 2. So we have 0, 1, 2. This is the third item in this data set here. If we were to look at what that looks like, what it looks like is it is numbers, and 0 if that pixel is just blank, completely white. Then if that pixel is darker, it can be anywhere from 0 to 254, and different shades of darkness because it's handwritten depending on how hard you push. Well, we can take this information here. So we're taking these pixels, these 784 pixels, and we're going to reshape them. So we're using numpy here to reshape it, and we're using numpy command called ravel, and it's going to take this information and it's going to reshape it so that it's 28 by 28. So we're creating the image here by reshaping this information. And then we can use our matplotlib, this IMShow. We saw that once before. We'll see it again when we plot with linear programming. But we can use the command IMShow and do our example image. It's been reshaped. And then our color map is going to be binary, just shades of white and black. And then we'll turn the axes off because that's irrelevant, and then we'll show the plot. So what we have here is that this data here that is pixel 1, 0, pixel 780, 0, creates this image that's a handwritten 4. Another example, let's take example 2. This is going to be from our data set. We'll take index location 5, so it's actually the 6th row here. And then we will say, okay, give me that data. You can see pixel 1 is 0, pixel 2 is 0, 784 is 0. We can reshape it. So it's 28 by 28 using reshape and ravel. And then we can plot it with IMShow and our binary color map. And we see that that particular picture makes a 2. What we want to do is create an algorithm that identifies that this picture is a 2 and the other picture is a 4. Now, this is coded data. We have the labels, so we're using a classification model in order to do this. So we already have within this data set, not only do we have the 784 pixels per image, but we also have that these images are all labeled. We already have in that database that this one is a 2 and this one is a 4. Okay. So what we're going to do is we first need to figure out what number of components we can do our dimension reduction down to and maintain all of the variance, the variability in the data set. So we're going to start with the batch size equals none. You can specify the batch size. You can say how many it should bring into the system at a time. Remember, we're doing incremental PCA. So it's bringing in a chunk of data, trying to find the principal components, then adding in another chunk and another chunk. And it's doing this because the data set is so big. 10,000 entries, 784 variables. Okay. So we'll start with batch size equals none. We won't specify it. We're going to standardize it because that's good practice for PCA. These are already essentially standardized because everything is on a scale from 0 to 254. It's not technically necessary in this case, but we'll include it because it's good practice to do. So scalar equals standard scalar, scalar.fit transform. That's going to turn this into an array. Then we're going to specify our range that we're checking. So we're going to go here. We can make a range from 100 components. So think about 784 pixels. So let's go from 100 pixels to, and we'll go to 784. That's the number of pixels currently, plus 1. So go right, because it's up to but not including. So if you want to stop before 785, then we want to make sure we go past that. And we could choose to do this because, you know, what's the difference between 770 and 771, right? So why don't we do this and we can just choose what increments. So right here, what I have is start at 100, go up to and include 784 by doing that plus 1. And maybe let's do it in increments of 50 because, you know, there's no difference between 95 and 97. You can tweak this. You can change this to something else. I encourage you to not just leave this to do 101, 102, 103. It will take forever. Okay, so let's do it, let's say, in increments of 50. All right, so this is the loop we had before. This is the explained variance ratio. Start with an empty list for num and nuns or I and nums or whatever you want. This time we're doing incremental PCA. Incremental PCA has the extra piece of the batch size, right? Okay, so, and you could specify that batch size. Number of components equals, and then it should be this range that we're doing here. Okay, all right. We're going to fit it to our scale data, and we are going to then find that variance ratio and append it to the empty list. So we have the explained ratio variance. And then we're going to plot it. So loop. Incremental PCA is not defined. Well, that's because I probably did not create that package, right? I didn't actually, no check mark. It'll tell you when you screw up. So we need to make sure we import that incremental PCA, the standard scalar plotting and NP I already had running. All right, now let's try that. Okay, create my range, create my empty list, create my loop. So the longer the range and the smaller the steps or increments in it, the longer it takes to run it. And it will tell you on the left here how long it takes to run a particular set of code. because one of the things we're doing is we're trying to maintain the variability in the large data set so that it's faster to run our classification model or cluster analysis. So depending on what you have here, it might take a while. So rather than make you wait for a minute while we watch the scrolly wheel go around, I'll pause the video and then we'll resume once it kicks in. All right, so it took 52 seconds for that to complete. So hopefully on your computer, it took less than a minute as well. Now we can plot that information. So what we can see here is that 100 components gets us 75% of the data. 150 gets us just short of 85. So if we see here, 200 components gets us 90% of the variance in the data set. So we would be fine with 200, 250, 300 components, okay? Because as we look at these pictures, so let's go back to this picture here, there's not different colors to it. It's all just grayscale. There's big chunks of white. And so it should make sense that it should be able to go with a much lower number of principal components than the number of 784 variables. When you start adding color, when you fill up the entire screen with image, then the number of components is going to be much higher. All right, so let's go with 200. So now that we've identified the appropriate number of components here is 200, let's do our incremental PCA. So we're going to do IPCA equals incremental PCA number of components 200. We will fit and transform using the scale data. So what we've done is we've taken our giant data set and we have taken our 784 variables and now we have reduced it down to 200 variables. So now that we have that, we can use our classification or our cluster methods depending on what we're trying to accomplish. Here, let's use a classification model and let's use our K nearest neighbors. So I refer you back to our video on K nearest neighbors. So what we're going to need is we're going to need from sklearn.neighbors import K neighbors classifier. And from sklearn.metrics, import the accuracy score. So here we're going to be able to figure out, did it appropriately recognize the number? Now this is a multi-label K nearest neighbors because it could identify the image as a 1 or a 2 or a 3 or a 4 or a 5 or a 6 or a 7 or an 8 or a 9. So there are 9 different labels. I can't remember if there's zeros in there. I think there's 9 labels in there. That it can identify, right? So we can't use precision or recall. We can only use accuracy score. So we're going to use accuracy score to see if it correctly identifies the handwritten digit. Now, we had 10,000 rows to our data. So let's separate them into X train and X test. So what we're going to do is we're going to take 8,000 and it's going to be our training data. And then the remaining 2,000, right, we like our 80-20 rule, is going to be our test data. So that's what this code right here says. It says X train is going to be the first 8,000, and then X test is going to be 8,001 to 10,000. Okay? All right. Oop. Make sure you run your nearest neighbors too. All right, so we got all that. Now, inside the MNIST data set, there's also something called target, and that target is going to be the labels. So we're going to call Y the targets from MNIST, and we need to pull these to match. So the Y train is going to be the first 8,000, and the Y test is going to be that remaining 2,000 between 8,001 and 10,000. So we need the labels that go with them. All right, now we need to do our K nearest neighbors. And remember, with the K nearest neighbors, we need to identify how many neighbors we are going to do. Are we doing 3? Are we doing 7? Are we doing 10? Here we have what do we have? 200 variables now. And we have 10,000 as our data set. So we could probably get away with a lot higher nearest neighbors. But we want to make sure we connect all these nuances of the difference in our handwritten numbers. Only slight differences in some of these numbers. So let's go with a lower one. It will mean that this will run a bit slower. So we might want to explore changing that k nearest, the number of k here. All right. So now let's do so we've called our classification model. We have fit our classification model. And now let's get it to predict. Okay. All right. So what it's predicting is that, remember, there's 2,000 in our test here. It's predicting the first one is a 6, the second one is a 2, the next one is a 0, so it is 10 labels, sorry. And so we could check the accuracy. So when it looks at these predicted values versus the actual values, it is 94%, 93% accurate, right? That's pretty good. So it's able to identify the picture as a particular number. It's telling us that that is 93%. Okay. All right, what have I changed here? So what we're going to do then, sorry, I got a little bit carried away with myself. The one we just did not use our principal component analysis. So I just realized here, what are we doing? So realized here that I wrote X new, and that was for the incremental one. So what we just ran here was the full data set with the full 700 whatever variables. Oh my goodness, my brain is not working. The full 784 variables. So if we do the full 784 variables, we get an accuracy of 93%. Now, what I'm trying to show you is that if we use our principal component dimension reduced data set, we want to see how accurate the prediction model is there. So this X, the incremental PCA used one with the 200 components, we label that X new. So notice this was just X. My apologies. All right, so if we want to do a comparison, then we look at here, let's make the X train X test based on the new dimension reduced data set. So rather than X, we're using X new that ties to this incremental PCA one. All right, so let's try that. All right, X train X test. So we've separated out the data set, the reduced one. And then we do the exact same process. So we're going to call our k nearest neighbors. We're going to fit it. We're going to predict the values. And then we test the accuracy. What we should have is that it should run faster. So notice this said 1 second, which, is not the end of the world. And this one said 0 seconds. It is faster with that dimension reduced. And the whole point of this is to make this more easier to process without losing a bunch of the accuracy. And you can see here we go from 93% accuracy to our dimension reduced version is at 90.6% accuracy. So we only lose a little bit there. And if you're concerned that you have lost that, so let's say it's bigger, that's a bigger deal, then you can keep more of the components rather than going to 200. Maybe you keep 300 components. And in fact, just for fun, let's do that. 300. Okay, so now we have X new based on 300 components. So I'm going to go back down and we're going to rerun this. And then we're going to rerun this and fit, predict. All right, the accuracy when we had 200 components was 90.595. Now let's run this. Interesting. Okay, and it went down. So we can run them a couple times and see. There's a bit of variability, right? Every time you run the model is going to come up with be slightly different depending on its iterative process. So it's interesting. This one's slightly lower. Maybe we have some noise in there that's creating issues that is reduced with that simplified component. But we can see how much of it we can retain with that principal component analysis. We did incremental here. In our next video, we will look at the other versions of PCA. So there is what is called sparse and kernel. So we'll look at those in the next video.